everyone to the new season of VSET. Before I introduce today's talk, I'm gonna already advertise next week's talk, where we have Lea Nagel presenting Designing Simpler Mechanisms, Transparency, and As-If Dominance. Okay, so let's go to this week's talk. So this week we are very happy to have James Best presenting the paper Divide and Confer, Aggregating Information Without Verification. And we are also very grateful to our panelists, Dimitri, Migrow, and Nemanja, Antić, who are here to ask questions. So we don't have co-authors here today for the chat, so if anybody in the audience wants to ask an urgent question, just go ahead and unmute yourselves, and afterwards there's also time for more discussion. All right. So yeah,
thank
James,
you very much for
go ahead.
Thank you very much for having me. So this is joint work with Daniel Quigley at the University of Oxford and Maryam Saeedi and Shourideh, who are colleagues here at Carnegie Mellon. A fundamental question in economics is how efficiently do various institutions aggregate information dispersed among large populations? And there's lots of papers which show we can almost perfectly extract information from informed parties, even when there are large conflicts of interest. And these are in environments as diverse as eliciting expert opinions, voting rules, common value auctions, unconstrained mechanism design. All of these approaches to getting perfect information extraction rely on at least one of the following features. Cross-verification, which is where we cross-check people's reports against one another, and we punish disagreement as evidence that people are lying or being dishonest. That one would actually go towards the picture that you chose for this talk, where the elders are interrogated by Daniel when they make their false accusations, and he finds out that they're lying by seeing conflicts in their reports and gives them an outcome that they do not want as a result. And often these cross-verification approaches might be twinned with rewards for agreement as well. This is well understood as something that allows us to extract information effectively. The other feature that is used, particularly when looking at large populations, is informational addition. And that is where they unboundedly increase the available information in the population by taking the population off to infinity. What does that mean? It means that if we take 0.1% of the population, as we take the population off to infinity, that 0.1% of the population has all of the information you need to make the best decision possible. And so that means an institution that throws out the voices of 99.9% of the population would still be able to get a very efficient outcome. This is what I refer to as informational addition. We're interested in an environment where neither of these two forces are present. So our paper is going to look at a stylized model. This is not a piece of applied theory, where a decision maker or receiver wishes to elicit information from senders with whom she has a conflict of interest. In this setting, the sender's information sets do not overlap. One person's information tells them nothing about another person's information. And this means there's no hope of verification. It's not going to be possible to tell if one person is lying by comparing their report to another's. And then the other feature is we're going to look at informational division. That's going to be where a fixed amount of information is divided among the senders, and we're going to be interested in taking the number of senders, the informed parties, off to infinity. So we're going to look at information being divided very finely across a large population. Both of these concepts are going to be made more concrete shortly. And we're going to examine this in the context of transfer-free mechanism design, where we're going to be looking to maximize the decision makers' payoffs. And by solving the mechanism design problem, that's going to tell us the upper limit of how well we could aggregate information in this setting. And the questions we're going to ask is, with no hope of verification, can informational division benefit our receiver? What does the optimal communication protocol look like? And can we achieve the decision maker's first best outcome as n goes to infinity? The answer to the first question is that the receiver strictly benefits when information is divided very finely. Oh, we have a question. Oh, no, that's just the slides.
Sorry, it took me a while to find the workaround.
No problem. The answer to the second question is that the optimal mechanism is a surprisingly simple solution. We'll define simple later, which is going to be reminiscent of a two-tailed hypothesis test. It's going to reject out in the tails. And finally, we're going to see that the optimal mechanism, because it punishes suspicious consensus in the direction of the sender's bias, we're going to burn surplus and get an inefficient second best solution. And so the contributions of this paper are to introduce a new way of thinking about information aggregation in large societies, this notion of informational division rather than informational addition. Then we give a methodological contribution is we develop tools for studying large population mechanism design via the notion of incentive compatibility in the large. That is a notion that we introduce in this paper. And we're going to use those tools to characterize the optimal mechanism when information is divided among a large population. And the inefficiency that we find demonstrates that information aggregation in large populations is going to, the efficiency of it is going to depend on the nature of information in the limit of the population. For it, in this case, whether we're looking at informational division versus informational addition. And the reason we think that that's important is because it raises questions about how we think about informational aggregation in all of these other settings, whether they're looking at it in common value auctions or markets or voting mechanisms. In those settings where they're finding efficient information aggregation, it's in the presence of informational addition, and our result is suggestive that there may be lessons to be learned by re-examining some of that literature through the lens of informational division or some more general framework for thinking about information in the limit. Okay, now to clarify all of this, let's start with a simple, small population example of informational division. And we're going to call our receiver a CEO for this little example. And the CEO is going to choose whether to accept or reject a new project, where accept is equivalent to choosing A equals 1. And the value of this project is going to depend on a cost shock and a demand shock, each of which is observable to a department manager. Now, the shocks are uniformly and independently distributed on negative, 0, and positive. The independent distribution means that the cost shock tells us nothing about the demand shock and vice versa. The CEO's payoff, should she accept, is just the demand shock minus the cost shock, which we'll call the value of the project. And the manager's payoff is from accept is the value of the project plus 3. This ensures that our managers always want the project to go ahead, albeit they do prefer all else equal, they would prefer the project to go ahead when it's high value than when it's low value. but they do always want the project to go ahead. And the CEO is going to commit to a direct mechanism, sigma, which is going to assign the action, A equals 0 or 1, as a function of reports C tilde D tilde. And of course, she's got to respect incentive compatibility with this mechanism. So here along the x-axis, we have the value of the project, and along the y-axis, we have the probability that the project takes on one of these values. Our CEO or receiver's preferred allocation is going to be reject whenever the project has negative value and accept when the project has weakly positive value. By contrast, our sender preferred mechanism, our managers, is to accept whenever the value of the project is greater than -3, which is always in this case. So it's always accept, as represented by the red line. Now, let's first think about the case where the information is not divided, but just held by a single manager. A single manager observed the demand shock and the cost shock. Unsurprisingly, our receiver cannot do better than the sender preferred allocation here. Why? Well, the sender knows the value of the project perfectly and is the monopoly information source. So the sender will always report the value of sigma that maximizes the probability of accept whenever the value of the project is greater than -3, which in this case is always. And so this is very bad for our receiver because in this case, the sender preferred allocation is completely uninformative and she's getting no information at all. She would be indifferent between this and never taking the action, never approving the project. However, when we divide the information between two senders, suppose there's two managers, one who observes demand and the other observes cost, we're going to be able to do better. Here is one simple mechanism that does better. Right? We say this mechanism is simple because the outcome depends only on the payoff relevant state, the demand minus cost. It improves the CEO's payoffs, right? They're getting information now. She now rejects whenever she wants to reject. And she's sometimes accepting when she strictly wants to accept, albeit not as often as she would like. It's bound away from her first best because of this surplus burning at the top. Sorry, can I ask, can you see my hand on the screen? Good. Okay. This is incentive compatibility here is guaranteed by these two pivot points for our sender. What do I mean by this? Well, an upwards lie by the sender is pivotal in two cases. If the true state is -1, an upwards lie is going to shift the reported state to 0 and increase the probability of accept from 0 to 1, which benefits the sender. But if the sender exaggerates upwards and the state is 0, then it's going to increase the reported state to 1, which is going to reduce the probability of accept from 1 to 1/3, which is going to cost the sender. It so happens, trust me, that these two, this cost exactly offsets the benefit in this case. Now, this simple mechanism that just depends on the payoff relevant state, that restriction to simplicity is a restriction. What do I mean? Here is a picture of our mechanism where on the x-axis we have the demand shock and on the y-axis we have the cost shock. And this is our mechanism here, which is giving us the same probability of accept along each ISO value line for the value of the project. For example, let's think about this one here. This is the value of the project is 0. We're assigning the same probability for all cases when the value of the project is 0. Our manager who observes the demand shock in this case is choosing a column of probabilities of acceptance for the different realizations of the cost shock. Okay, so that's choosing between this column, or this column. Because this mechanism is simple, we can't vary the payoffs from choosing from these different reports independently. What do I mean? Well, suppose I wanted to change the payoff from reporting the 0. Well, if I change this, that would require me, if I wanted to reduce, say, the payoff, the probability of acceptance when both people report 0, I would also have to reduce the probability of acceptance when one reports -1 and the other reports 1, and vice versa. Okay. And it turns out this is going to be costly. The optimal mechanism is complex. The optimal mechanism reduces the probability of accept when both people report 0. And that is going to reduce the payoff of reporting the middle column without also reducing, whilst keeping the payoff of reporting low the same. Right? We've not changed the column of probabilities for the -1 report. This slackens the IC constraint of the low type sender and allows us to make improvements elsewhere. I'm not going to get into the nature of the improvements elsewhere. I don't want to dig down into exactly why this complex mechanism is optimal. It's a bit complex. The reason it's not very complex is because we've got 3 types in here and 2 senders, and so we can see it nice and easily on this picture. Right.
James, can I ask a question?
Yes.
So before you introduce this complex mechanism, going back to a simple case, which I think I understand better, it seems crucial there, which you kind of hinted at by saying, oh, you choose columns and I guess the other side chooses rows, that the 2 sides do not know or see. So I don't know what you reported before me reporting mine.
Exactly. This is the word divide is doing lots of things in this in this talk, unfortunately. So yes, the information is divided both in the sense that each person observes their own unique piece of information. They don't observe the information of anyone else. Moreover, their unique piece of information provides them no information about other people's information.
Okay, and this is going to be true throughout the paper, say
throughout the whole paper. Yeah. So this is the no hope of verification part of the paper, is the fact that nobody knows anything about the information of anybody else, and that means we can't cross-check one person's statement against another person's statement to see if they're lying or not, even in a statistical sense. Okay.
James, can I ask you,
yes,
just to understand the improvement of the complex mechanism of this optimal simple mechanism, if you go one slide, if you could go one slide forward. So here, essentially, you're decreasing the probability in the middle, right, to 3/7. And so you're saying it somehow allows you to increase the probability where the receiver finds it better or optimal to 5/7, right? Because it was 1/3. So this is where the improvement comes from. Is it roughly?
Yes. So by not restricting ourselves as simple mechanisms. We can target incentives more precisely by each report or independently each report. Here we by reducing the middle report, the probability of accept for the middle report, we reduce the payoff from reporting middle without reducing the payoff from reporting L. That gives us a bit more slack in the IC of the L type. And we use that extra slack to increase the probability of acceptance when we strictly want the action to, when the receiver strictly wants the action to occur, when the state is 1. Now, it so happens that this change messes up the incentives of the medium type, so we have to make a further change to restore those incentives. It balances out, but I don't want to delve down too deeply to that. What's going on here is it's just allowing us to more effectively screen people by their types by giving us the freedom to adjust the mechanism, right? And so we're going to look at this in the large. We just saw that dividing information between two managers, it can benefit the CEO, even though the information about demand and cost was not cross-verifiable. We couldn't cross-check people. But in general, for a finite set of senders and a general type space, I should just say general type space, not large type space, we might not always be able to get a strict improvement for the receiver for a fixed N, for a fixed N, I should say. And kind of more importantly, the optimal mechanism may be extremely complex. If I'd have given you a richer type space with two senders, you know, computationally, we get these very ugly, complicated looking mechanisms, which is kind of bad news for us. Our analysis is going to be on large populations. So we're hopefully, and I will, spoiler alert, we will get around this problem of complexity as we go to the large, as we increase the number of senders. Okay. So the general model that we'll use to analyze this, there's going to be n senders and a single receiver. The receiver faces a binary decision, accept or reject. Each sender observes a private signal. The signals are IID. They're drawn from a finite type space, T1 to TK, which is increasing, they are increasing in the index. And they occur, each type occurs with probability F1 to Fk. Right? And this is our vector of probabilities. We're going to normalize the expected value of a signal to 0 and the variance of the signals to 1. And now we're going to introduce our payoff relevant state. I'm going to circle back to this payoff relevant state in a second, but just I'll state it for the time being. It's omega is going to be equal to the sum of agent signals divided by root n. And that's going to be important, we'll see. Okay, and our receiver's payoffs is just going to be the action times by the state plus some preference parameter R. And the senders is the action times by the state plus a preference parameter B, where this preference parameter B is greater than the receiver's preference parameter R and also greater than 0. This implies our sender is biased in favor of A equals 1. Or in favor of accept, we might say.
James?
So, yes.
So just
hi.
Hey, so because so since you've only assumed the sort of the moment normalizations on the distribution, I just want to kind of clarify the sense in which we should think of this as, you know, we're not changing the information in the system as we vary n. Should I think of it as because omega's distribution is going to settle down to something? It's not literally that things are the same when there's one agent or three agents, but I should think of it as 1,000,000 agents versus 1,000,001 agents. It's basically the same distribution of omega, and so I should think of it as not changing how much information is in the system for that reason.
Thank you. Yes. Yes, exactly. Exactly. So I will tell you. I will come back to that comment at the end of this slide. In fact.
Oh, okay.
But no, because it's yes. So our notion of informational division here is going to be, by defining our state in this fashion, it implies as n grows, the aggregate uncertainty remains constant, and each sender becomes less informed about the state. Indeed, they become completely uninformed as n goes off to infinity. And it is true that strictly speaking, the information, not strictly speaking, it is just true that the information isn't really staying constant as we increase n, as Elliot pointed out. The variance is staying constant, but the information is moving around in some sense as we increase n. As n gets very large, which is where we're going to be interested in, it's going to become as if we are just dividing information ever more finely. In fact, it would be as if we were, no, I'm not going I removed a picture from this slide, which was a picture of a Brownian motion, and a Brownian motion that terminates at some time t. And you can think of informational division as n gets large as we are dividing that Brownian motion into smaller and smaller increments, and each sender is just observing the movement, the direction of movement of that Brownian motion in their increment. And we're taking that increment ever smaller as n goes off to infinity.
Actually,
does that answer your question, Elliot? Oh, sorry.
I was going to ask, so are you thinking of a Brownian motion, or is it really a Brownian bridge? So does it start somewhere and then you're dividing a, say, unit interval of some realization of Brownian motion? I guess I was hoping for more details on the Brownian motion construction. I saw that you mentioned also in the paper, and now I'm wishing you put that slide in. So what does it look like exactly?
So this would be a Brownian motion. The way in which I was describing it is it would literally just be a Brownian motion. It ends at some point cap t. And then you divide that into increments, and each agent is observing the movement in their increment. And that's our information structure would be equivalent to that in the limit.
Okay.
Now, there is something about Brownian bridges that can be said later on, but not with respect to this exact point. And I probably want to avoid it entirely, but we could talk about that offline. Just for the sake of time. Thanks. Okay. So this is our notion of informational division. We've got a fixed variance, which is that's staying constant, but we are dividing the information up amongst the senders. And this is best for thinking about the large n limit in the division in the large n limit. There's a different way one could model the whole thing, which we are not going to do, but that might happen in the future, where it would be more precisely the information stays exactly constant as we change n, but that will be for a different problem. Okay, of course, the fact that the signals are IID means that one agent's report cannot be used to verify the report of another. So we still have this feature of there's no hope of cross-verification. Okay. So We're going to consider a mediated communication game, where a mediator commits to a communication mechanism that maps reports into a recommended action. Sender reports their type. The mechanism recommends an action to the receiver chooses the action, and we only allow for mediation. There's going to be no transfers. So,
sorry, James, the receiver cannot commit to action based on reports you're saying, right? So there is the receiver is decision maker.
Yes, it's going to turn out that because we're maximizing the receiver's payoffs, the obedience constraint's not going to bother us.
I see. So it's equivalent.
We can come back and verify that at the end, but so our problem is going to be to maximize the receiver's expected payoff, the expectation of the probability of accept times by the state plus their preference parameter, subject to a truth-telling constraint and an obedience constraint. I'm not going to give the math for this because we're immediately going to change our problem. This is the direct problem. It turns out that direct mechanisms are going to be a bit unwieldy for our large N analysis. And our solution is going to be to reframe the problem in the frequency domain. That's going to be the frequency. The mechanism is going to depend on the frequency of each type, each report type. So, for example, this here, HK of S, is the normalized empirical frequency of type K. So what's this saying? This is going, this is the realized sample frequency of people of type K, and it's distance from the population frequency, and we're multiplying it through by root n for reasons that will become apparent. And I'm going to often, whilst this is a normalized empirical frequency, I'm going to often just refer to it as a frequency. And this is the vector of these frequencies. Now, because it's without loss of generality to restrict attention to symmetric mechanisms, it's also going to be without loss of generality to restrict attention to mechanisms that only depend on frequencies. I don't have time to get into the reasons why. They're not that complicated. And so we're going to consider mechanisms which are just a function of the realized empirical frequency of each types. Okay, I'm going to give you a I'm going to give you a picture in 2 slides. So why are we wanting to look at this frequency domain, frequency approach? Well, first, the domain stays constant even as n gets large. So it means our mechanisms are going to be acting on the same domain, Rk, in fact, Rk minus 1, I should say, independently of the number of senders. Whereas if a direct mechanism, our domain would be exploding in n. Also, in the limit, as n goes to infinity, these empirical frequencies are going to behave very nicely. They are going to be distributed normally with a variance-covariance matrix, which I will come back to in a second. And the state, which is just equal to the normalized empirical frequency times by the vector of types, is also going to be distributed normally with mean 0 and variance 1. Our incentive compatibility condition in this case is going to look slightly different from the standard one, but not that different. So here it's going to be the expected value of the sender, the expected payoff to the sender, conditional on reporting their true type, has got to be greater than or equal to the expected value of the sender, conditional on reporting some other type, S tilde I. Right? And we see here what's S tilde I going to change. It's going to change the reported, it affects the distribution of the reported frequency, but of course it has no effect on the actual frequency of types.
Sorry, can I just clarify?
Yes.
So this H tilde N is going to be the H of N minus I, and only differs for the H of N subscript I. Is that what we're saying, or is it more complicated?
Correct. For a fixed N, that's correct, right? Yes,
Yes.
we're going to be we're just, if you lie, you're going to be switching you're going to be decreasing the frequency of one type and increasing the frequency of another type by a small increment.
Okay.
And so if we go back to the frequency domain in the case of three types, our three-type example here, we have the frequency of people who got no shock, and here's the frequency of people who got positive news. And we don't have the frequency of people who got negative news, because these are deviations of frequencies from the population, and so they're all going to sum up to 0. So H0 and H1, they pin down H-1. And these are our ISO density contours, and we see that there is a negative correlation between the reports of H1 and H0, because if somebody reports H1, that means that person is not reporting H0. Or if somebody's reporting positive news, they're not reporting negative news. And in this space, these are our ISO state lines here. They've got this slope of -0.5. And a simple mechanism, one that just depends on the state, would be constant along these ISO omega lines. So what's an example of a simple mechanism? Well, this is the receiver's preferred allocation. Of course, this is not an incentive compatible allocation, but it would look like this. This says except for everything above whenever the project has a value greater than 0. This is the sender preferred allocation, except whenever the project has a value greater than -b in our frequency domain. Okay. Now, to characterize incentive compatibility in large finite populations, we're going to look at the limit. And to do that, we're going to continuously extend the set of mechanisms obeying our frequency incentive compatibility constraint to the n=infinity limit. Right? And to do this, we're going to compare our mechanisms in terms of their outcomes. What do I mean? So for some mechanisms, sigma n, and the associated n sender normalizing nef hn, they're going to induce some joint outcome distribution over the action an and the realized empirical frequency. And similarly, for the limit case, some mechanism sigma and the limit nef h, that's going to induce a different joint outcome distribution, which for each action and realization of the empirical frequency. These outcome distributions associated with the mechanisms, they're going to fully determine the players' payoffs and their incentives. So we can think of those as the important object as the relevant object. Now we're ready to define our notion of incentive compatibility in the large. A mechanism, sigma, is incentive compatible in the large if there is a sequence of incentive compatible n sender mechanisms sigma n, whose outcome distributions converge as follows. The outcome distribution, the outcome of hn converges in distribution to the outcome distribution associated with sigma. So we're just really very loosely, I would like to say, although it would not be quite accurate, a mechanism sigma is ICL if there is a sequence of incentive compatible n-sender mechanisms, sigma n, which converge to sigma, right? And here we're saying their outcome distributions converge to the outcome distribution induced by sigma. That's the only, right?
Why would you?
Yes.
Why are you using a stronger notion of convergence here? So you're using convergence and distribution only for these mechanisms. What would happen if you insisted on a stronger notion?
Well, the proof's much longer and uglier, and we ended up finding that we had to impose some restrictions on the number of discontinuity points. We had to have a zero measure of discontinuity points in the limit mechanism.
Did you look at like
L
LP
infinity.
or L infinity? Okay.
Yeah.
Okay.
Okay. Thank you. That was there was a lot of that. Yes, and that is exactly why I can't say sigma n converges to sigma.
Yeah.
Okay.
It would be
however, the outcome distributions are the relevant object in terms of they determine the payoffs, they determine the incentives. They're the thing that we really care about. I suppose the issue is that if I start
it might be nice
playing
to say
around with the distribution of the frequency independently of the mechanism, then it might matter. But however, when we're thinking about the optimum in that case, it would matter for the optimum as well. So if you're happy with that, if you're not happy with that, we can definitely get into a discussion of it at the end. Okay. Okay. So our first theorem is a methodological contribution, which is to characterize the set of ICL mechanisms. So the ex-ante, we're going to define the ex-ante payoff of a sender at the n equals infinity limit by this U, and that's just the payoff of a mechanism for a sender from some mechanism sigma who doesn't have any information. It's an uninformed sender. And we say a mechanism sigma is ICL if and only if the derivative of utility with respect to a frequency hk is equal to the unconditional probability of accept under that mechanism times by type tk. This is the limiting analog of the envelope formulation of incentive compatibility familiar in the mechanism design literature, where we have the evolution of payoffs with respect to type on the left, and on the right, we have the marginal information rent. What's different to standard mechanism design problems is this marginal information rent's linear in type. Right? It's not entering into the expectation of the probability of accept. No, it's not conditioning on anything here. The reason it's not conditioning on anything here is because in the limit, our agent has no information. And the second condition is essentially the interim monotonicity constraint, which says that a higher report induces a weakly higher probability of acceptance.
James?
Yes.
So Are you further claiming that this thing is differentiable, or is this all in the same sense as what you have in the selling a good problem, where it's that by convexity this thing is almost everywhere differentiable, and you're requiring this condition wherever it happens to be?
So it turns out that this is equivalent to this envelope condition. It's equivalent to a problem in which you have an uninformed sender who can nudge the distribution by HK in any direction, right? And that object is differentiable, and it'd be the first order condition of that problem, of an auxiliary problem. And that turns out that that's going to be that's the correct way to discipline the limit of this problem.
But that problem, you're saying it is like genuinely differentiable as opposed to this being a subgradient condition.
Exactly. The problem that I described just then, that one is differentiable. In fact,
your notion of limits is weak, and so it might not preserve differentiability in the limit. Sorry to harp on about that. We can go on about it later.
Yeah, I don't have a good answer to that off the top of my head.
I think with stronger notions of convergence, it would preserve it, but for here, it's not obvious at all.
I'll tell you that object that I describe here is not part of the proof of theorem 1. So it's an interpretation of theorem 1. So, and there is this equivalent problem to this problem here, right? Which is an uninformed sender who can pivotally nudge the reported nef by this small amount dh tilde k in any direction k. They would not wish to do so. The first order condition from that problem is the same as is the same as this envelope condition here. Right? The way we get to this envelope condition is not by just taking a derivative. At no point are we taking a derivative to get this condition in the proof.
Right. You have this perturbation argument with nearby. Is that right? Maybe you're going to do the proof sketch.
I was looking at the time. I'm not going to do the proof sketch, I'm afraid. I want to explain what the result is, and so the thing that is the interpretation of this result is the correct discipline for a large finite n problem. We're wanting to approximate large finite populations, right? And we're going to approximate them by looking at a limit problem. The limit problem that we want to look at is not just going straight to n equals infinity and looking at the n equals infinity sender. That person has no impact on the distribution of reports, and they have no private information, and anything goes in that problem. It turns out the correct discipline is to still treat them as uninformed, right? But treat them as if they can have a small impact on the distribution of the reports nonetheless. That's the one that's captured by this envelope condition. And then the monotonicity condition says, and it's got to be robust to small amounts of private information in a second order sense, small. Okay. Visually, it's saying that our sender, an uninformed sender living at 0 here, wouldn't want to nudge the distribution of reports that direction, and they wouldn't want to nudge the distribution of reports upwards either. Okay. Our new problem is much simpler, right? So we can now approximate the optimal mechanism for large finite populations by solving this much easier problem, maximizing receivers' payoffs subject to these set of linear constraints in linear equalities in the envelope condition and our linear monotonicity constraints. A much easier problem to solve. And before introducing our optimal mechanism, I'm going to say, just remind ourselves that our definition of a mechanism being simple is simple if its outcomes only depend on the payoff relevant state. And our theorem says that a simple mechanism is optimal. In fact, it is this interval mechanism here, which recommends except if and only if the payoff relevant state is in some interval omega-1 to omega-2, where the lower threshold is in between the sender's bias and the receiver's preference parameter, which we're setting equal to 0 to make life easy here. And the upper threshold is above the receiver's preference parameter. So this is and I want to give us some intuition for why this thing is the optimal mechanism.
But James, kind of for clarification, so you gave two examples at the start, simple mechanism and more complicated mechanism. This more complicated mechanism, you're saying, does not really matter, right? Because it is as if the agent is uninformed, so operating on the prior, essentially, but still can have an impact on the distribution. So it means conditional on the state. I guess I'm not learning anything about what Nemanja or you have as signals. So you can focus on types of mechanisms in this first part of the example, right, and not the second part. So essentially, that is
so I'm going to give you the intuition as to why we can focus on. In fact, I'm going to give you the intuition for this mechanism in 3 steps. So why is the mechanism incentive compatible in the large? It's going to use double pivot incentives similar to the 2-sender example. Why are intervals optimal among the simple mechanisms? So assuming it's a simple mechanism, why is the interval mechanism optimal? And it's going to be because surplus burning punishments at the top are going to be optimal, also like the 2-case example. Why are simple mechanisms optimal in the limit? And that's going to be because the sender is uninformed in the limit, unlike in the example, right? And I will make that intuition slightly more solid as we go. And yeah, I think I've got time. So first, incentive compatibility and pivotality. So in our limit problem, the sender is uninformed and his reports are small, but our envelope condition still treats them as if they can have a small impact. And so if our sender lies upwards, they nudge the reported state upwards, and that's only going to matter at the lower interval, where they can nudge the report above the threshold that induces acceptance, and they want acceptance because the value of the state, the lower threshold, is greater than -b. And so they benefit from that nudge, but it can also nudge us off the top step, the higher threshold, reducing the probability of accept when the state is much higher, when they would like the action most. And what the incentive compatibility condition here for any interval mechanism is incentive compatible, not just the optimal one, if this is satisfied. The density at omega-1 times by the payoff of the action at omega-1 is equal to the density of the omega-2 times by the payoff of the action at omega-2 plus at omega-2. Okay. And also, because the density is higher at omega-1 than at omega-2, this is going to imply that monotonicity follows as well. Okay, so that's incentive compatibility in this case, nice and easy. Why do we have an interval mechanism? It's going to be because it's valuable to punish at the top. So first, consider how we might improve. We're going to consider how we might improve on the sender preferred allocation, right? That would be the best we could do in the hypothetical case where a single sender observed omega. But when information is divided among lots of senders, what we're going to do is we're going to look at a perturbation to a nearby interval mechanism. So this is our sender preferred allocation, right? Jumps up at minus b, except whenever the state is higher than minus b. We're going to start by considering, let's just increase that lower threshold a little. Well, the sender doesn't have a huge value for the action at that lower threshold, so it's not going to have massive incentive effects on our sender, but it's still going to violate the incentive compatibility of our sender. We're going to need to restore incentives. How are we going to restore incentives? We're going to restore incentives by introducing this threshold at the top. Now, the effect of this threshold at the top is to create a cost of a lie, right, of lying upwards by d omega tilde. Right, if I lie and I end up in this region, which happens with this probability, I'm going to lose the action, and that's going to cost our sender. And we need that cost to be high enough to get our preserve the incentives, right, to stop us wanting to lie up. But this cost, this threshold is going to create a cost for the receiver. But the cost for the receiver is not going to be the cost that occurs under lying, it's going to be the cost that occurs under truth-telling, which is going to happen with a much lower probability. Indeed, as that upper threshold gets very, very large, the relative likelihood of us going over the threshold under a lie versus under truth-telling becomes incredibly large, right? So the punishment, the cost of the punishment for the sender, for the receiver, the cost of the punishment for the receiver becomes incredibly small relative to its incentive impact on the sender. And this is reminiscent of the Merlisian moral hazard approach to moral hazard in Merlis's 1975 paper, where he makes the observation that you want to punish out in the tails because it's the highest relative likelihood under a deviation out into the tails. And so it's efficient to punish out in the tails. However, unlike the case of Merlis, we can't get full efficiency, because in the moral hazard problem, you can increase the punishment that you ascribe to a particular event. Here, there's no transfers, so the punishment is the removal of that event from the action space. And as we want to increase this lower threshold further, we've got to keep reducing the upper threshold. Okay. Finally, why can we restrict attention to a simple mechanism? So take some optimal ICL mechanism, sigma H, and consider collapsing it down to this simple mechanism, which gives for each value of omega, gives the same conditional value probability of accept. Obviously, the receiver's payoffs are going to be unchanged. The only issue is whether it preserves incentives for the sender. But in the large, the sender is uninformed, and this envelope condition, it's going to deter every local perturbation of the NEF in every direction. This implies that it's also going to deter simple deviations, where the sender just shifts the reported state omega tilde by d omega, but in a fashion that keeps the distribution of the reported frequencies conditional on the reported state constant. So we can do it in a way that preserves the conditional frequencies. And so that if we do that for our uninformed sender, this simple deviation, it changes the probability of acceptance in state omega under our simple mechanism that has collapsed our mechanism down. It changes the probability of acceptance in state omega from sigma hat omega to sigma hat omega plus d omega. Okay? Well, that means, given that it wasn't incentive compatible for them to make that simple nudge, that in the full mechanism, it is not incentive compatible for them to make that simple nudge in the reduced mechanism. And I'm going to try and illustrate that with a picture and then close, if that's okay. So,
James, someone wants to ask you a question. I think Evgeny, he raised his hand.
Oh, yeah.
Oh, sorry.
Yeah, just didn't want to interrupt, but small question. So, am I correct then that in your introductory example, the only reason that you had this probability 1/3 rather than 0 on the upper side was that your state space was too small? So like you would want to move the threshold a bit more upwards and there have this sigma equal to 0, but you couldn't because
I can't answer that with certainty. I can't answer that with certainty. I think I think you're right. So when we look at continuous type spaces, we always seem to be able to do everything with 0, 1, but we didn't prove that we could always do everything with 0, 1.
Like, so just to understand, so the idea is that in your general framework, your result is that like this sigma equal to 0 on the upper in the upper tail is an optimal mechanism, right? So like there could be other ones that do just as well, but the structure is a bit different. Or
it's almost everywhere unique, this mechanism.
Okay.
Okay, so for a given omega, we have a conditional distribution of the types H0 and H1. I just want to illustrate the point on the previous slide in the 3-type case. As omega varies, so does the true conditional distribution of the empirical frequencies. So suppose omega was equal to epsilon. And not every nudge that you might make would preserve that empirical distribution of frequencies, right? In fact, most deviations won't. If I nudged the distribution to the right, then the distribution of the reported empirical frequencies, the probability would be centered here, right? And we'd get too many H0s in this case. But there's always going to be a simple nudge which mimics a true shift in the state, right? And then because our envelope condition deters all deviations, including this simple one, it's going to imply that this collapsed simplified mechanism is also going to be incentive compatible as well, because in that world, the only deviation you can make is a simple one. So our uninformed sender, there's no scope for using higher orders of the frequency distribution to screen more efficiently, and that means we don't have to deal with complex mechanisms in the large. Okay, and I would really like to say just these last 2 slides, and then I've got 30 seconds. So this is a subset of the related literature. This is the literature where we have additive information and shows that we can get first best as n goes large. And our paper is different from this literature because the information is divided. First best is not attainable, but we can characterize the second best solution. So that's our contributions relative to that literature. And I'd like to summarize this paper. So what are the important things, I hope, for people to take away, if anything's important? We've introduced this notion of informational division to thinking about large society aggregation problems. We've developed new tools for studying large population mechanism design via the notion of incentive compatibility in the large. Now, we've not shown this for all possible mechanism design problems with large populations. We've done it in a particular example, but there's nothing particular about incentive compatibility in the large as a notion. Theorem 2 characterizes the optimal population for large populations. We show it's simple, an interval mechanism is optimal, and importantly, I think most importantly, our payoffs are bounded away from the first best, even as n goes to infinity. Why do I think that's most important? Well, because it demonstrates that information aggregation in large populations is inefficient when we consider informational division rather than addition. And that suggests that it may be valuable to revisit information aggregation in other settings through the lens of informational division, or some more general framework of information in the limit that nests both division and addition. Okay, thank you very much. Sorry for going over.
No worries. Yeah, thank you so much. So yeah, we still have a bit of time for discussion. So I would start with the panelists if you have any last comments or questions, and then we will see if we have time for other people. So yeah, whoever wants to go.
So yeah, I think it's really nice paper because it kind of gives new perspective, right, on information aggregation problems. It says, well, if it's about divisibility between, you know, larger and larger population, then we might get this inefficiency. So I wonder, because there are different forces at play. So do you think that kind of a transfer freeness or unverifiability or informational division itself is the main contributor to the inefficiency in your framework?
Okay, so what you gave me 3 options: transfers,
yep,
unverifiability, and division.
Right.
So I'm going to take them in reverse order. In our setting, if we had practiced informational addition, then we would have approached first best, even without verifiability. Why? Informational addition would be just taking the sum of signals. In our setting, it'd be equivalent to taking the sum of signals. As n goes off to infinity, the problem of you being in the region where there's a disagreement about whether to accept or reject goes to 0, right? And so the sender preferred allocation would converge in payoffs to the receiver preferred allocation. So if we had cross verifiability in our setting, that's a nuanced question, because one way of modeling this would be everybody gets an unconditionally independent signal of a state variable. As n goes off to infinity, we're going to make those signals less and less informative about that state variable. And so in the limit, not only are they going to be conditionally independent, they're going to be unconditionally independent, and therefore there won't be any cross-verifiability. However, you could have conditionally correlated signals and take n off to infinity. So we could make those signals less informative about the state as n goes off to infinity, but you could say group people into classes, and some people are getting, you know, our signals are collectively getting really bad for any of these subgroups, but they're highly correlated with one another. What happens in that environment? Really not sure. You know, there is a paper to be written on a general framework for nesting the various ways of thinking about taking information to the limit in large populations, and that's one of the issues you would have to deal with. Then when it comes to transfers, yes, I keep, you know, we you know, it's not going to go into this paper because the referees have not asked for it, thankfully. But we do keep wondering, what would be the optimal mechanism with transfers, and watch some space. I'm sure that's going to, it's going to be very natural to expand questions to those kinds of environments. Does that answer your question?
Yep. I just think, you have this interesting economic message of surplus burning at the top. And with transfers, is not obvious that survives, right? So that's...
Yeah, especially since we've got risk neutral. We've got linear payoffs. I think that probably might be able to get us efficiency, right? Well, okay. Really off the cuff. Please don't put any weight on this. Our claim is that actually at the limit, our sender is essentially uninformed and can nudge this distribution. Well, what does that sound like? That sounds like a moral hazard problem where I can take some action which nudges the distribution of outcomes. And if we were to add transfers into a moral hazard problem where our payoffs are linear, then we sell the firm, right? And we can get efficient outcomes. If we made our agents risk averse, then I suspect we might end up in Merlis's world, where we get the unpleasant theorem of there is no optimum, and you push all the punishment out into the tail and get arbitrarily close. But that is maybe a conjecture.
Thank you.
Yeah, so really nice paper, really enjoyed it. I think this idea that we should think more about how we take large population limits is important, and you could do various versions of this. You could separate scaling preferences of the receivers and the senders. There's a lot you could do also in between the additive version and the device version. But one of the things I'm still sort of want to understand a bit better is the relationship between theorem 1 and 2. So what I'm wondering about is the simple interval mechanism that you find in theorem 2 for large infinite populations, can we say whether that's approximately incentive compatible even with large enough n? Or can we say whether it's approximately optimal with some notion of correlation?
When you say approximately incentive compatible, I want to make sure I'm on the same page. This means that I'm within my IC is within epsilon of some epsilon. Take some epsilon for large enough n. IC is going to hold with respect to that.
Can I make a statement of that type that, if I fix that mechanism you say is optimal in the limit, can I find, for any epsilon I like, can I find a population large enough so that it's epsilon IC? I guess my whole thing with these two theories is I'm trying to understand a little bit better the relationship between the aggregate outcomes that you showed the convergence of and the mechanism itself. Anyway,
so
that's
okay.
That's sort of my big picture question about the paper. Yeah.
Okay. So what I can say is, if you take a complex mechanism and simplify it, collapse it down to a simple mechanism for fixed n, and we start taking n large, that will become approximately incentive compatible for large n. That simplification becomes approximately incentive compatible for large n. And there is we don't state it as a result in the paper, but we state that as a remark, actually. But I do not have a result. We do not have the result that says for a large enough n, incentives will be give me an epsilon for large enough n, IC will not be violated by more than that epsilon. I feel like it should be relatively easy to prove those. So maybe we should prove that. But we haven't proven it. So I don't want to say that we have shown that. What have we shown? We have shown that there will be a mechanism which has, for a large enough n, there will be a mechanism which has almost identical outcome distribution to that, which is strictly incentive compatible. And it feels like a hop, skip, and a jump away to show that that's going to imply that the incentives are not going to be violated by a significant amount in that case. But it's not proven.
Yeah, no, I mean,
so,
I asked because it seems
very
plausible.
Good, very valid, important question. Yeah,
I asked because it seems plausible, and if it's true, it would be a nice result to have, even if it's just a discussion.
Okay, thank you. That's yes, that was very useful. Okay, great. Let me. Okay.
All right, so maybe I take this quick break to finish the official part. So yeah, thank you everybody for coming. Thanks to James and our panelists for participating. And yeah, to the attendees, come back next week for Lea Nagel